My mind wasn't really into it, so I was screwing up before, but let's take a look at a couple of these integrals. We've got some indefinite integrals and we've got some definite integrals. So we're going to go through these pretty quickly. So in this case, we're still on indefinite integrals. 4x plus 5 raised to the negative 3 dx. And this looks like a simple polynomial with a u substitution. So we go u equals 4x plus 5, and du equals 4 dx, and dx equals du on 4. So we end up with 1/4 u to the minus 3 du, and that's equal to 1/4 times u to the minus 2 on minus 2 plus c, and we substitute back in, minus 1/8 u, that's 4x plus 5 to the minus 2 plus c. Similarly, we've got another integral that we're going to do. We have 2x plus 1 raised to the 97th power. I don't know why they gave this as an example, but again, we use u equals 2x plus 1, and du equals 2 dx, and then dx equals du on 2. So we have 1/2 u to the 97th power du, and this is 1/2 u to the 98th power over 98 plus c, and that's 1/96, and this is 2x plus 1 to the 98th plus c. So we're just continuing with our indefinite integrals and using u substitutions. But now we're going to do definite integrals. Now definite integrals, that means that if we have a function, we've already seen this, f of x, and we want to evaluate that integral on 2 points. It's going to give you the area under the curve. We saw that with the Riemann the Riemann sum, the fundamental theorem of calculus. But basically, what we have is a to b. Always write the smaller one down below and the larger one on top. F of x dx, and that's equal to g of x evaluated between b and a, and that's going to be g of b minus g of a. And that's how a definite integral is evaluated. So let's take a look at an example. We're given sine of 3x cosine of 3x dx between 0 and pi on 2. And so we first want to substitute the arguments of the trigonometric functions. U equals 3x, and so dx equals du on 3, and that's equal to 1/3 0 to pi on 2 sine u cosine u du. But here we've got another substitution. We say z equals sine of u, dz equals cosine u du, and we have basically a polynomial integration. And we just say a to b here because we don't know what those limits are if we converted them. I go back to the original functions and then I plug in the original limits. That makes it easier for me, less confusing. Other people do it other ways, but I don't do it. It's not as intuitive. So we have z dz, and that's equal to 1/3 z squared on 2 plus, and that's evaluated, between the limits a and b. Okay, so actually that's 1/6. 1/3 times 1/2 is 1/6. 1/6. And z squared is sine of u, and then when we do all of our substitutions, we have sine squared of 3x between pi on 2 and 0. And this is equal to 1/6 times sine of 3 pi on 2 minus sine squared of 0. And we know that is 0, and this one's -1. If we go back to our knowledge of trigonometric functions, we've got pi on 2, pi, 3 pi on 2, and this is 0. And sine of this is -1. So -1 squared is 1 times 1/6, so our answer is 1/6. So that's a good that's a good example of a definite integral. And we got a couple more here that we can choose and give as examples. Here's one between 2 and 5 on the x-axis, dx on 3x squared. We don't even need a substitution here. We just go equals 1/3 2 to 5 x to the -2 dx, and that's equal to 1/3 x to the -1 on -1, evaluated between 5 and 2. And this is equal to -1/3 times 1 on 5 minus 1 on 2. And then when we get the common denominator, we have -1/3 times 2/10 minus 3/10, and that is, or 5/10, I'm sorry. Oh, gotta get that. Let's get that correct. Minus 5/10, and that's equal to -1/3 times -3/10, and that's equal to 1/10. You have to be careful with your signs. That's the trick to these, is be very careful about how you evaluate these. Now here we have a last example, 0 to 1 on the x-axis. We got dx over x squared plus 10x plus 25. Well, here we realize that that function is equal to x plus 5 times x plus 5. So it's a square. And we got x squared plus 10x plus 25. That's what that is. So we have 0 to 1 dx over x plus 5 squared. We can use a u substitution. Plus 5 du equals dx. And then we have a simple a to b u to the minus 2 du. And this turns out to be u to the minus 1 over minus 1, evaluated between b and a. And plugging back into the original function, we have 1 over x plus 5, and this is a negative sign, between 5, or 1 and 0. And this then is minus 1 times 1, 6 minus 1/5. And then if we get the common denominators, we have minus 1 times 5 thirtieths minus 6 thirtieths, and that's equal to minus 1 times minus 1/30th, and that gives us a positive 1/30th. Again, it's all, you got to pay attention to how you are evaluating. Now we're moving into some really interesting stuff. Inverse trigonometric functions. Hello. Hi. Do you mind if I do this a little? Or I'll go in the other room. I'm just going to be about 10 more minutes, and I'll go in the other room.
No, you didn't do it. I'll just search for something.
No. I'll go in the other room. I'll just take 10 minutes.
All right.
All right?
Okay.
It's not going to be long, I promise.
All right.
I really wanted to get to the inverse trigonometric functions. They're really cool. It just take a minute.
Okay.
I promise.
All right.
Yeah. All right.
There you go.
Thank you. It doesn't look like as nice a day as yesterday.
No.
I hope it doesn't rain. I hope not. I haven't looked at the weather. Okay. So, let's okay. Now, we're going to look at something that's pretty cool. We're going to look at inverse trigonometric functions, and we're going to use a technique. Now, it's not so obvious here, but this is called integration by parts, and we're going to introduce the concept. Whoops. Wait a second. We're gonna introduce the concept. Let's say we have two functions, u and v, and we take the derivative of u and v. Well, if we do this derivative, it is derivative by parts. So we take the derivative of u first and then the derivative of v. So we end up with v du plus u dv. And then if we take integrals, d u v equals v du plus u dv. And let's say we want to find that integral. So all we have to do, and we know that this is u v equals v du plus u dv, and swapping things around a little bit, we have v du equals u v minus u dv. And this is a very important technique. This is what we call integration by parts, and we're going to be using it. Integration by parts. And it's a very, very important method. Powerful. So, having introduced that, let's move to our inverse trigonometric functions. So, we're going to start out with the inverse sign. So, these are inverse or arc signs. Okay, so we start out with y equals the arc sine of u. And then that means the sine of y equals u. So we draw our right triangle, and we got y. So that means u over 1, and this is 1 minus u squared. And that's because we got a squared, let's say x squared, plus y squared equals r squared. R is 1 in this case, and y is u squared, and x squared, and then x squared equals 1 minus u squared, and x equals 1 minus u squared. So that's how we get the bottom there. Just for refreshing, it's simply the Pythagorean theorem. So we do our derivatives. We go d du sine of y equals d du of u, and we have cosine of y dy du equals d du of u, and that means dy du equals 1 over cosine of y. But also dy du equals d du of sine, the arcsine of u. So that is equivalent to d du arcsine of u. And now we put everything into original variables and switch things around. So let's put d du of arcsine of u equals 1 over the cosine of y. But the cosine of y equals 1 minus u squared. So 1 over cosine of y equals 1 over 1 minus u squared. So that's what this is equal to, 1, the square root of 1 minus u squared. So that's our derivative of the arcsine. But then if we multiply across by du, we go d arcsine of u equals du over the square root of 1 minus u squared. And then if we take our integrals like that, we end up with du du over square root of 1 minus u squared equals the arcsine of u plus c, because that's what that's what that term turns out to be. So now we have a new integral, and that's pretty cool. And we can do the same thing for the cosine function. So whoops, what am I doing? All right, that's what I wanted. Okay, so, whoops, alrighty. So let's take a look at our cosine function. So let's say y is equal to the arc cosine of u, and cosine of y equals u. And so we again go to our trusty right triangle. We have our angle y and u over the hypotenuse, and that means we have 1 minus u squared for the sine, and we take our derivative, d well, we can do it implicitly. Let's just do it that way. It's minus sine y dy dx du equals d du of u, and that equals dy du equals minus 1 over sine of y. But dy, remember, dy equal du is equal to d du of the arc cosine, my goodness, I'm not paying attention. All right, arc cosine of u. So that's what that is, du arc cosine of u. But then, if we switch things around, du of arc cosine of u is equal to, again, minus 1 over sine of y. So we got minus, but 1 over sine of y equals 1 minus u squared. So we have 1 over 1 minus u squared. And that's our derivative. We did these earlier. But then we have d cosine, arc cosine, equals minus 1 over square root of 1 minus u squared du. And if we take the integrals, we have, swapping things around, minus du over square root of 1 minus u squared equals the arc cosine of u plus c. So here we have, this is pretty cool. Now we move on to even more complex trigonometric functions. Here we try the secant. This is pretty cool. Secant, y equals a secant, or arcsecant. Let's give ourselves some room here. Okay. Y equals the arcsecant of u, and secant of y equals u. So here's our angle y. Now, remember the secant is 1 over the cosine. And it is equal. Boy, what's going on here? Is my pen? Secant. Let's try it again. There we go. I don't know why it's working that way. I fully charged it. Equals secant. Sometimes I have to reselect the pen. Secant y. So 1 over the cosine of y. The cosine of y would be a, b, and r. Okay, so a squared, a over r. A over r is the cosine. So r over a is the secant, and that's equal to u. So r must be equal to u, and a equals to 1. So that's u, and that's 1, and that's equal to the square root of 1 minus u squared. And let's just make sure, because we got a squared plus b squared equals r squared. Wait, what's going on here? Alright, r squared. And if we have r is u squared, and a is 1 plus b squared, b is equal to u squared minus 1. So I gotta correct that. It's good to check yourself sometimes, because it's so darn easy to make a mistake, and there I did. So it's a good idea to work through all these things carefully and checking yourself. So b is u squared minus 1, because we worked it through. R is u, a is 1, a squared plus b squared is r squared, and we substituted in. So yep, this is it. So now we can get on with our problem. Our derivative of secant y is secant y tan y from our trigonometric dy du equals d du of u. So dy du is 1 over secant y tangent y. And also we know from up here that dy du is equal to d du of the arcsecant of u, and we plug that in. So we have 1 over secant y tangent y equals d du of secant, the arcsecant of u. And now we fill in d du of arcsecant of u equals secant of y would be u over 1, so 1 over u. We got 1 over u times u squared minus 1, because tangent is u squared minus 1 over 1. So 1 over the tangent would be that. And so we have our derivative of the arcsecant function. But then again, if we go d arcsecant of u equals du over u square root of u squared minus 1. And if we take our integrals, we have du over u times u squared minus 1 equals the arcsecant of u plus c. And that is unimportant derivative. That's where you get all those crazy derivative or integral relationships. So I just wanted to make sure that I had this correctly. It looks like I did. I just want to make sure. Squared minus 1. Yep, that's it. Yeah, I got it. Got it there. Everything's copacetic. And so let's take a look at the next one, which is our tangent, arctangent function. This is pretty cool stuff. And it's so much better to be able to derive it using a step-by-step thinking process, logical process, and working through the problem, being able to set the problem up correctly. And that helps you find errors like I made. You can easily get distracted when you're trying to make a video that while you're talking, it's a little hard. You know what? There was a study done about this idea of multitasking. And people really don't multitask. We do singular tasks one at a time. It's just that we switch back and forth. But we're only really completing one task at a time. That's all our attention will allow us to focus on. There's no such thing as the person that is processing 5 different things all at once consciously. It just doesn't happen. So here we go. We say that the tangent of y equals u. And that means on our right triangle, it's a little simpler for us than the secant. So u over 1. And then this is mu squared plus 1. And now we get to it. We go take our derivative, which we've done many times before, so I'm not going to go through it step by step. Well, yes. We have the sine u over cosine, or y over cosine of y. And then we do our differentiation. We got d dy is equal to, all right, minus sine y over cosine squared y times minus sine y plus 1. And that's equal to 1 plus tangent squared y, and that's equal to secant squared y. So that's our derivative. I don't know, I just felt compelled to go through the derivation so that I guess we refresh ourselves. It's been a while since we did integration or derivatives of tangent. So our derivative of the tangent function is secant squared. Secant squared y dy dx equals d du of u. So dy dx equals 1 over the secant squared of y, but then dy dx, or du, why am I saying dx? This is wrong. This is u. Oops. du. So you got to be careful. I'm not even careful. All right, so dy du is equal to the du of the arctangent of u. So that's what this is, the du of the arctangent of u. And then we can swap sides around. Du arctangent of u is equal to 1 over the secant squared of y. But the secant of y is u squared plus 1. So 1 over secant y is 1 over u squared plus 1. So this is 1 over u squared plus 1. And that's a square, so there's no square root. And so we have our derivative of the arctangent function. But then let's say we have d tangent arctangent of u equals du over u squared plus 1. And then we took our integrals and we swap sides. We got du over u squared plus 1 is equal to arctangent of u plus c. And that's our answer. And see if we have any more of those. Yes, that's valid. All right, we got more. We got the cotangent and so on. So, you know what? We're gonna wait until the next video to do. We're gonna do the cotangent, our cotangent, our cosecant, and then we're gonna use our trusty formula for integration by parts.